Dear students, our module 6 is Numerical Methods 2. The first session is Solution to Linear System of Equations. In this module, we have two methods for solving a system of linear equations: Gauss elimination method, which is a direct method, and Gauss Seidel iteration method. So we start with the Gauss elimination method. Here we consider a linear system of three equations in three unknowns x, y and z. a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. For solving this system of equations using Gauss elimination method, first we form the corresponding matrix form. The matrix form of this system of equation is a1 b1 c1, a2 b2 c2, a3 b3 c3 into x y z equal to d1 d2 d3. This is the matrix form of this system of equations, where the first matrix, that is the 3 by 3 matrix, a1 b1 c1, a2 b2 c2, a3 b3 c3 is the coefficient matrix, and d1 d2 d3 is the constant matrix. The matrix form is ax is equal to d. Now we form a new matrix called augmented matrix AD, and this augmented matrix AD is constructed by inserting a new column d1 d2 d3 to the right side of the coefficient matrix A, and that column matrix is the constant matrix D. Now transform the augmented matrix to upper triangular matrix by elementary row transformation. So using elementary row transformation, the augmented matrix becomes a1 b1 c1 d1, that is, there is no change in the first row. In the second row, the first entry is 0, that is, we convert a2 to 0, and b2 become b2 dash, c2 become c2 dash, d2 become d2 dash, and similarly we convert the first two entries of the third row to 0, and c3 becomes c3 double dash, and d3 become d3 double dash. Now the augmented matrix, we convert it into the system. It becomes a1 b1 c1, 0 b2 dash c2 dash, 0 0 c3 double dash into x y z is equal to d1 d2 dash d3 double dash. Then from this reduced system, we solve or we find out the values of x, y and z by back substitution. In the same way, we have to find the solution of a system of equation in 4 unknowns, 5 unknowns, etc. The method will fail if any one of our constants a1, b2 dash or c3 double dash becomes 0. In such cases, rewrite the equations in a different order so that a1, b2 dash or c3 double dash are non-zero. An example for solving a system of equations using Gauss elimination method. Apply Gauss elimination method to solve the equations x plus 4y minus z is equal to minus 5, x plus y minus 6z is equal to minus 12, 3x minus y minus z is equal to 4. The equations are written as x plus 4y minus z is equal to minus 5, x plus y minus 6z is equal to minus 12, 3x minus y minus z is equal to 4. A system of 3 equations in 3 unknowns. For solving this equation, we have to find out the values of x, y and z. The matrix form of the system is the first row of the matrix is the coefficient of the first equations 1, 4, minus 1. The second row of the matrix is the coefficient of the second equations 1, 1, minus 6. The third row of the matrix is the coefficients of the third equations 3, minus 1, minus 1 into x, y, z is equal to, the right side is minus 5, minus 12, 4. Now we form the augmented matrix, which is the matrix constructed by inserting a new column, which is the constant matrix minus 5, minus 12, 4 to the right side of the coefficient matrix A. So the augmented matrix is 1, 4, minus 1, minus 5, 1, 1, minus 6, minus 12, 3, minus 1, minus 1, 4. Now we transform the augmented matrix to an upper triangular matrix using elementary row transformation. Here the first entry in the first row is 1, which is a non-zero entry. Then using that 1, we converting the remaining entries in that column to 0. That is, we have to changing 1 to 0 and 3 to 0. So for the operations for changing this 1 to 0 is R2 minus R1. Since 1 is in the second row, so for 1 to 0, the operation is R2 minus R1. And 3 is in the third row, so for converting 3 to 0, the operation is R3 minus 3R1. So using this elementary row transformation, the matrix becomes 1, 4, minus 1, minus 5. There is no change in the first row. In the second row, using the elementary row transformation R2 minus R1, the matrix becomes 0, 1 minus 4 is minus 3, minus 6 minus minus 1 is minus 5, minus 12 minus minus 5 is minus 7. In third row, the operation is R3 minus 3R1. So 0, minus 13, 2, 19. So the matrix is not an upper triangular matrix. So now we fix the leading entry in the second row as minus 3 and then convert the minus 13 to 0 using elementary row transformation. So the elementary row transformation for minus 13 to 0 with respect to minus 3 is R3 minus 13 by 3 into R2. Then the matrix becomes, there is no change in the first row and second row. Now the third row is changes to 0. So the second entry becomes 0. Then 71 by 3, 148 by 3. Now we write the system as, the system becomes 1, 4, minus 1, 0, minus 3, minus 5, 0, 0, 71 by 3 into x, y, z is equal to minus 5, minus 7, 148 by 3. Write the equations. X plus 4y minus z is equal to minus 5, minus 3y minus 5z is equal to minus 7, 71 by 3 z is equal to 148 by 3. So from the last equation, we have z is equal to 148 by 71, it is 2.0845. Now we substituting the value of z in the second equation. Minus 3y minus 5 into the value of z, it is 2.0845 equal to minus 7. So y is minus 1.1408. Then substituting the value of y and z to z in the first equation. So we have a x plus 4 into minus 1.1408 minus 2.0845 equal to minus 5. And solving, we got x is equal to 1.6479. So the solution to the system are x equal to 1.6479, y equal to minus 1.1408, and z equal to 2.0845.